How is everyone today? So you get to hear with some algebra magic, somehow. Of course, that's what we're going to talk about today. Once you're able to carry out moving from the left-hand side to the right-hand side, which is a purely algebraic technique, if you're able to do that, then now you can continue this antiderivative and say, well, that antiderivative, whatever it is, surely has to be this one, the antiderivative of this thing. And the reason why that's nice is because the antiderivative distributes across the subtraction. You can factor out the 2, and then this is a fairly straightforward use of the logarithm rule. Okay, which is to say that I guess being a little careful. Since I did it fast last time and I got some Gesundheit, some questions, distributing the antiderivative and factoring out the 2 gives us that antiderivative, and then subtract this antiderivative like that. And then, ignoring everything but just that, if you really felt unsure or at any rate so inclined, you could do a substitution. You could say u is x minus 1. Then if u is x minus 1, du is dx, so that this is 1 over u du. And what's the antiderivative of 1 over u du? Natural log of absolute value of u. As a result, this is 2 multiplied by log of absolute value of x minus 1 minus what?
Minus log of absolute value of x.
Very good. And then plus a constant. So a few things after thinking about how Friday went and listening to some of y'all later had questions and asked some questions. So in the first place, I want to point out that I write my ones like that. That's kind of weird, right? Most folks don't do that. But to that end, by way of explanation, I ask, what does that mean?
Absolute value of -1.
Really? Because I meant 1 minus 11.
But your ones are not like that, right?
Which is the point. Don't worry, you couldn't have got it right. I just would have said the other one. Right? Whichever one you said, I would have said the other one. Okay. Whereas this can mean only one thing, right? Okay. So what I'm telling you is that it's a good idea for your ones to look different than your absolute value bars. Yes?
Yes, I was just wondering about that. Could that be also slightly misinterpreted as a 7?
Conceivably. And it's a good point. So for that reason, the way I write a 1 is thus, and the way I write a 7 is like that. I mean, because I agree entirely. It's possible. Other questions? Okay. Now, listening to y'all and asking about this. So here's a thing. Is that in differential calculus, you learn the following: that the derivative of the logarithm of x is 1 over x. Okay. So you learn that. And then in consequence, okay, if you wanted to, in a sense, take this, imagine this to be an equation, that here's a function, here's another function, and then that's a thing that we're doing. If you want to solve for logarithm of x, you kind of want to get the derivative to go to the other side. Okay, so then to that end, it kind of seems like you should write that the antiderivative of 1 over x dx is a logarithm of just regular old x. So it kind of seems that way, right? Because if it's logarithm of just regular old x for that one, then Why the change? Why is it that when you're viewing it from the antiderivative point of view that these show up? Okay, it's a valid question, and so I'm going to address that because with many of you, y'all are like giving me like googly eyes every time I say no absolute value. All right. So to that end, please consider is that let's calculate what is the derivative of the logarithm of, say, 5 times x. Well, if that were exactly x, then the answer would just be 1 over x, right? But it's not. So in fact, we're taking the x, and before it is given to the logarithm, we first fiddle with it. First we multiply it by 5. So because we're doing something before the x gets to the log, that means that we have two machines chained together. So what rule will we need? The chain rule. So according to the chain rule, this should be 1 over 5 times x, and then multiplied by the derivative of 5 times x. Now, what's the derivative of 5 times x?
5.
It is 5. So this would be 1 over 5 times x, like that, and then multiplied by 5. And then, what? Right, then it's just 1 over x. Now, wait a second. That's curious. Okay? Because if the derivative of the logarithm of 5x is 1 over x, that's the same as the derivative of just logarithm of 1x, right? So I claim that, at least at first blush, until you think about it, this should be kind of curious. Because do you observe that, in fact, there's nothing special about 5 except it's constant with respect to x? I could have put a 55 or a 55 million. I could have put anything. But the reason why that's totally reasonable is that you know, from your algebra days, you know something about the product concerning logarithms, products, and sums. Specifically, you know that the logarithm of a multiplied by b, like that, is what? Right, it's the logarithm of a plus the logarithm of b. Logarithm says that that's the case. So as a result, what's the logarithm of 5x? What is another way to write it? Right. So you could say that the logarithm of 5 times x, like that, is the logarithm of 5 plus the logarithm of x. Now, is 5 a constant?
Yeah.
Surely, right? How about the logarithm of 5?
It is constant.
It's constant. If that disturbs you just a little bit, then, well, on my calculator I'll type logarithm of 5, okay, and then get that number. So I have a question. If we table the question for just a week, and then I come back and then type logarithm of 5 again in the calculator, what number will I get? That number, right? I mean, surely. It's a constant. So concerning that, what's the derivative of logarithm of 5? The derivative of this? 0. That's why it goes away. Right? So the derivative of this one is 1 over x. The derivative of that one is 0. All right. Fine. Now, what does that have to do with this absolute value business? Well, consider that, in fact, what we're saying is that the derivative of, well, let's do one more. How about the derivative of the logarithm of negative 3x, like that? What will that be? Now, here's the deal, is that notice that this logarithm rule cannot be used, at least not directly. The reason why is that this logarithm rule right here says that you can do this, it's permitted that you can do this, so long as a is greater than 0 and b is greater than 0. Okay, so you can't use the logarithm rule here because it's you can't say logarithm of negative 3. Nevertheless, you can still use the chain rule, okay? And this would be 1 over negative 3x multiplied by the derivative of negative 3x, which is negative 3, which is, of course, 1 over x. Still works. So what I'm telling you is that, in fact, it is the case that the derivative of the logarithm of k multiplied by x for any k whatsoever that's not 0 can't be 0 because then this would be exactly logarithm of 0, but that's not defined. So all that I mean is that it's permitted that k be positive or negative, either one. What's the answer?
1 over x.
1 over x. Because if you care to do it the third time, you'll get 1 over kx multiplied by the derivative of kx, which is k because k is a constant, and then the k's cancel because k is not 0. All right. Then, because that is the case, please remember that the definition of absolute value of x says that, well, in the first place, if x is greater than or equal to 0, if this is true, then what's the absolute value of x?
X.
Just x itself, right? And then if x is less than 0, what's the formula for the absolute value of x?
X.
No,
Absolute negative of x.
just negative of x. You can't put absolute value over here because we're defining it, right? Can't be in here. Now, wait a second. Can negative x be positive?
It's absolute.
Is it possible for negative x to be a positive number?
Yeah.
Yes. Yes. Okay, so let me say this out loud. It's kind of disturbing. The absolute value of 8 is 8. The absolute value of negative 9 is negative 9. Okay? So is it permissible for negative x to be positive? Sure. When x is negative. If x is negative 11, then negative x is 11. All right, fine. So I want to say that you could just as well write it like this. You could say that, I'll write it like this. I'll say that, notice that the output of absolute value is always the input, and it has to be multiplied by something. In this case, it's you multiply the input by 1. And in this case, you multiply the input by negative 1. So do you observe that the way that the output of absolute value is made is it's always multiplying the input by some constant. It's either multiplying by 1 or it is multiplying by negative 1. Okay? So as a result, we can calculate what is the derivative of the logarithm of the absolute value of x. Well, there's two cases, right? There's two cases, in fact. So if you happen to be at a positive x, then what's the absolute value of x? Well, it'd be the derivative of logarithm of x, whatever that may be. This is when x is greater than 0. Okay, and then it's the derivative of logarithm of, well, if x is negative, then what's the expression for the absolute value of x when x is negative?
Negative times negative x.
It's negative x. Right? Now, what's concerning that the first one? What's the derivative there? 1 over x. So the derivative is 1 over x when x is positive. What's the derivative of the logarithm of negative x?
1 over x.
1 over x. So what we're saying is that, well, when x happens to be positive, the derivative is 1 over x. When x happens to be negative, the derivative is 1 over x. So in fact, the derivative is just 1 over x, right? In all cases. So therefore, the derivative of the logarithm of the absolute value of x is just 1 over x. And for reasons that aren't clear to me, many differential calculus courses don't go through this. But this is the reason why the absolute value is on the right-hand side of the antiderivative rule, because it is on the left-hand side of the derivative rule. Yes?
We took the derivative of elements negative x, you already took into account multiplying by -1, right?
Right. Because, I mean, are we in agreement here? Okay, so what I'm saying is that this is with k as 1. This is with k as -1. And in fact, any non-zero k is permitted, including 1 and -1. So so this is the real rule in a sense. Okay? And therefore, that's the reason why the antiderivative rule looks as it does. Good. So now that we're past that complication, we can move on to the algebraic rule. So the thing that we're doing today is purely an algebraic thing. Okay, there's no calculus to it, except that it is a rule that you'll end up using a great deal in calculus, but there's no calculus to it. So, in the first place, I'll repeat a variation of the remark that I made last time. So when you want to do this algebraic technique, which is called a partial fraction decomposition. So you want to take something that looks like this: n of x over d of x. Okay, and you want this to be a rational function. So in particular, that means that the numerator is a denominator and the numerator is a polynomial and the denominator is a polynomial. So that means that we're not talking about square roots and sines and cosines. We're talking about polynomial over polynomial. And then concerning these, you want to perform polynomial long divide n of x by d of x. When you do that, you'll be able to write down the equation that the numerator is equal to the denominator multiplied by the quotient plus the remainder. Okay, and in particular, this will be a polynomial whose degree, so the degree of the remainder has to be less than the degree of the divisor of the d there. So now all of these have names. So let's write down the names of these. So this is the divisor. This is the quotient. This one is the remainder. And this one, the dividend. Now, it is, well, it is. I view it as an unfortunate thing that these two things' names are so similar. But that's the way it is. So the reason in the end is that these suffixes. I forget. I think it's like not. I don't think it's English, but at any rate, the suffixes like end and or. They sort of imply the one that's doing, like the actor, and the acted upon. So divisor is the one doing the thing. The dividend is the thing that it's happening to. So like when you consider a plus b, It's plus that's doing the thing. And A and B are called add-ins. Add-ins. And when you're doing A multiply B, it's multiply that's doing the thing, that's performing the action. And then the A and the B, they're called multiplicins or something like that. Okay, whatever. So you do this. So suppose you do this. If you divide both sides of the equation by D now. Then the left-hand side is what you started with, right? That's what we began with. And then what's the right-hand side? So if we divide this term by D, what's left? Q of x. So that's just some polynomial, okay? And then right, R of x over D of x. So now this, because of this red condition here, that the degree of the remainder is less than the degree of the divisor, that means that this is now a proper rational function. So this is analogous to that thing you learned in grade school, you know, when the teacher said, you know, something like, you know, consider the number, say, 20 over 7. Is that a proper fraction?
Yeah.
No, not according to the grade school reckoning. In order to be a proper fraction in the grade school reckoning, the numerator must be less than the denominator. So like 20 over 7, not proper. Okay? So I'm trying to remind you of grade school. And this proper is not like an ethical judgment. It's just a name. Okay, so then, you know, the teacher says, you know, represent this as a proper expression. So 20 over 7 is not proper because the numerator's more than the denominator. So you could say that, oh yeah, in fact, this is, I could make 2 groups of size 7, so it will be 2, right? And then if you take away 2 groups of size 7, what remains? 6. So that you could write it like so. So an integer plus a proper fraction. So this is saying the exact same things about polynomials, is that every rational function can be expressed as a polynomial plus a proper rational function. And here propriety, properness, means numerator degree less than denominator degree. Okay? Good. So partial fraction decomposition, what it does is it acts on this. So you must do this first. You must perform a long division first, and then the decomposition occurs on that one. Okay. So now we'll have our first rule. Suppose that R of x over D of x is proper. And x minus c is a factor of D of x of multiplicity 1. Okay, so again, we talked about that last time, but could someone remind us, what does that mean? Right. When you factor it all out, it's going to be x minus c, and its exponent is going to be 1, not 2, not 7, you know. If it were 2, the multiplicity would be 2. If it were 7, its multiplicity would be 7. Okay, then the partial fraction decomposition includes something that will look like a over x minus c. All right. So now, this has been abstract for a few minutes, so now I think it's time to do something concrete. So here's an example. On the first page there, we considered this rational function. So x plus 5, and then over x squared plus x minus 2. So in the first place, is this a rational function? What does it mean to be a rational function? Right. So is it a rational function? And the answer is yes, because it's the ratio of two polynomials. Okay? So then now, because it's a rational function, we can ask the question, is it proper? So, yes.
Yes.
So why is it proper?
Degree is higher than the model.
Right. So what's the degree of the numerator? 1. What's the degree of the denominator? 2. And then now you go back to grade school in Ms. Harris's class and think, wait, was 1/2 a proper fraction? And the answer is yes. What about 3 over 3? Is 3 over 3 a proper fraction? No? 3 over 3 is not proper. Because remember that from grade school, every fraction can be, every fraction, integer over integer, can be represented as an integer plus a proper fraction. So 3 over 3 is 1 plus 0, right? So 3 over 3 is not proper. In order to be proper, the numerator must be strictly less than the denominator. So, you know, if I were to edit this and put a square here, so x squared, if I were, I'm not going to, but if I made that x squared, then would it be proper? It would not be proper. Okay? So it is proper. Yes, 1 over 2 and 1 less than 2. Okay? So then that means that we don't need to do a division. Okay? We don't need to do long division on this one. So we're given a rational function that is proper, which means that now we can proceed with the partial fraction decomposition. Now, to do that, we need to factor the denominator. So first we'll factor x plus 5 over x squared plus x minus 2, x plus 5. All right, and then it factors as what? As x plus 2, and then multiplied by x minus 1. So now, do you observe that, okay, there's 2 factors, and both of them have multiplicity 1. Okay, so because that is a factor of multiplicity 1, that means that, so what I want you to see is that because of this one, just this one, what am I trying to say? Because of just this one, this will decompose into what? So something over x plus 2. And then on the previous page, I wrote an a. Right? So I'll write an a because of that one. Now, what about because of that one? A similar deal, right? We should have another one, say b over x minus 1. Okay, and these are terms, so that means that they're added together. So because of that, something like that should show up, and because of this, something like that should show up. So what we have is we have an equation that looks like this: x plus 5 over x plus 2 multiplied by x minus 1. So the first part of the partial fraction decomposition is complete. So this is the pattern that is implied, or the decomposition implied. And what we must do now is we need to solve for a and b. All right, good. So now, the first thing I'd like for you to observe is that, well, what if I multiplied both sides of the equation by x plus 2? So what I mean to say is that, so observe that if I do this, x plus 2 multiplied by x plus 5 over x plus 2, x minus 1 equal to x plus 2 multiplied by a over x plus 2 plus b over x minus 1, what would be the virtue in doing that? Why would we want to do that? Well, there would be a cancellation, right? And there would be a cancellation. Okay? So if we do that, then, you know, the result would be x plus 5 over x minus 1 is equal to, now, this will just have a, right? So then it'll be a, and then plus, so this distributes to that one. Is there a cancellation for that distribution? There isn't one. So this would be plus b times x plus 2 over x minus 1. So if it was a good idea to do it with x plus 2, then what? Yeah, it's probably a good idea to do it with x plus 1, right? Okay. So then, sorry, x minus 1. So I'll just do that, okay? Because just without showing work, because I think you understand. If you multiply both sides by x minus 1, you get x plus 5 is equal to a multiplied by x minus 1 plus that x minus 1 cancels, and we get this. Okay. Everybody okay to hear? Yes?
That's your question. It doesn't matter which one you do first.
It doesn't. It doesn't because multiplication commutes. You could have done them, in a sense, both at the same time. And then when you're familiar with this, that's what you'll do. You'll just say, oh, you know, you'll have this one and say, oh yeah, the x plus 2s and the x minus 1s, blah, just, okay? So now, concerning this, there's two ways to proceed, okay? And depending on the problem at hand, sometimes the one way is better and sometimes the other way is better. So what I'm going to show you is I'm going to show two different ways to do this, okay? And when you're in the midst of a problem, you're going to have to decide which one you want to do. I'm not saying you must do both ways. All right, so one way to proceed from here is to collect on the right-hand side, which is to say that notice that the left-hand side, it's already simple, but if we were to multiply out and collect the right-hand side, what would be the coefficient on the x's? So we'd have ax plus bx. So how much x? A plus b. So it would be a plus b x, right? And then how much unit? How much constant? So we'd have negative a, and then
2b minus a.
plus, right, so plus 2b. So you could write it as 2b minus a. And so now I have a question for you. On the left-hand side of this equation, how much x do we have? We have 1x. And on the right-hand side, how much x do we have? We have a plus b. So if these are the same, and that's 1x, and that's a plus bx, then what's a plus b? 1. A plus b must be 1. Making this comparison. But that's not the only game in town, right? Because How much constant is on the left-hand side? 5. And how much on the right? 2b minus a, right? So what can we conclude about 2b minus a? That is 5. That must be 5. So now there's two equations in two unknowns, a and b. They're linear equations. So this is the kind of thing that you learned how to solve in what? Algebra? I don't know. So you could do it from here, right? Okay, like you could say b is 1 minus a, for example, and then plug it into there and then solve and blah blah. But here's another way, and this is on this particular exercise, this is a far more expedient way to go. So these, I'll refer to these as magic values. So what I want you to observe is that wouldn't life be a lot easier if, for example, say, we could just make that whole term go away? See, like there's two terms. There's the one that's involving A and the one that's involving B. And if we could just dismiss this one from any consideration, that'd be really nice, wouldn't it? So this equation must be true for all x, which means that it's got to be true even for like convenient, even magically convenient values of x, right? So because of that factor, what would be like a particularly convenient value of x? 1, right? If x were 1, then that whole factor would just evaporate, it'd be gone. So one of the magic values is 1. So when x is 1, the equation becomes, well, what's the left-hand side?
5.
When x is 1?
Oh, 6.
It'd be 6. That first term is 0, and then now this is 3b. Right? So what's b?
2.
So b is 2. Now you could say use this one now if you wanted. Because a plus 2 is 1, then a's got to be negative 1. But even if you didn't want to do that, what besides negative 1, what's another magic value? Negative 2 is a magic value. So in that case, what's the left-hand side? 3. And so that whole term goes away. This would be what? Negative 2 minus 1 is negative 3, so this would be negative 3 times a, and then plus 0, because that term is taken out. So then, as a result of this, what's a? Negative 1. So you could have taken this route. You could have taken this route. Either one would be fine. But in either case, you conclude that a and b must be thus. Okay. So then, as a result of all of this, we've determined that, in fact, you can decompose x plus 5 over x plus 2 times x minus 1. We said that it must decompose like this pattern, right? And we established that a is negative 1, so this would be negative 1 over x plus 2, and then plus b is 2, so this would be 2 over x minus 1. Now, is that what my friend said in the story of me talking about my friend? So is it? It is. Okay. I want to point out that I didn't do any calculus on this page. Right? So what I'm saying is that if it came to pass you were asked to anti-differentiate that, you would perform this this purely algebraic procedure, and then instead of anti-differentiating that, you'd anti-differentiate that. Okay, good. Let's do another one, or get started on another one. All right. Where are they? They're not, where is it? Huh. Oh, here we go. Okay. So, remark. So again, if we have r of x over d of x is a proper rational function, so it's a proper rational function. That means that we don't need to perform long division. If that's the case, and x minus c has multiplicity, say, I don't know. I kind of want to write n, just so it can be generic. But to make it sort of specific, I'm going to write 4. But understand that there's nothing special about 4. I could just as well write 5. Okay, then the following will be part of the partial fraction decomposition. You will have an a over x minus c, just like if it were multiplicity 1. But there's going to be several more. So instead of calling this just a, I'm going to call it a1. So a1, and in addition to that, you'll have an a2 over this thing. So it wouldn't make sense for me to just leave it there, because I could have just combined it with that one. In fact, you have to say this. Okay, then plus an a3 over this to 3, and then plus an a4 over this to 4. Okay, in practice, when we're giving you an actual exercise, then basically never do we go beyond 2, because otherwise it becomes just a mess. Okay, that you can't possibly fit on a page and a grader can't possibly grade. Okay, but understand that even if it said 44, there'd just be 44 of them. All right. Similarly, is that if something like a multiplied by x squared plus b is one of the factors. Is a factor of d of x. And I need to be clear here. So a prime factor. All right. So concerning integers, I could ask, like, what's the prime factorization, say, of 6? 2 and 3, right? What's the prime factorization of 7? Just 1 and 7, right? So in the same kind of way, polynomials can be factored, and some of the factors are prime. An example would be something like x squared plus 1. So x squared plus 1 is prime, and the best way to say it would be something like prime over the reals. Because, consider, does this factor in the reals? So can you write it as x minus something multiplied by x minus other something? You can't, because this doesn't factor, right? It doesn't factor in the reals. It factors in the complex numbers. It factors as x minus the imaginary unit, I, multiplied by x plus the imaginary unit, I. But you can't achieve that within the reals, so it's said to be prime over the reals. So in this case, if that's the case, then a times x plus b over a times x squared plus b is part of the partial fraction decomposition. Now, I know that we're coming up on against the clock, but I want to make sure that something is clear. So, ignoring the higher multiplicity terms, that a1 is a constant. Okay, And so that could be something like 5. Now, it's possible to consider the function like p of x equal to 5. For every x you input, out comes a 5. Now, is that a polynomial?
No.
P of x equal to 5 is a polynomial. It is. What's its degree? No. So we have to get this part so that this can be intelligible. So if I write p of x equal to 5, is that a polynomial? It is. Now, every polynomial has a degree. What's the degree?
0.
0 is a polynomial of degree 0. And what I want you to observe concerning these is that because a1 is a constant, that's degree 0, and what's the degree of that?
1.
Degree 1. 0 over 1. And if you have a degree 2 prime factor, then what's the degree of the denominator?
2.
And the numerator?
1.
1. 1 over 2. Now, one of the things that you learn in algebra is that concerning polynomials over the reals, every polynomial over the reals can be factored as a product of linear factors and prime degree 2 factors. So this tells you a complete description of how to do a decomposition. So bunch of those, and then you play this completely algebraic game, either by comparing coefficients or by using magic numbers. And on the complicated exercises, usually it's a good idea to do a combination of both. All right, have a nice Monday.